Hello, my name is Ling Xuanmeng. I am honored to present our latest work on ECCV 2024, Interclass Topology Alignment for Efficient Black Box Substitute Attacks. In the existing black box adversarial attacks, there exists a substitute attack strategy. It first trains a substitute model to fit the target model of the black box through a knowledge distillation paradigm. Subsequently, this substitute model is used in combination with white box adversarial attack schemes to generate adversarial samples. Finally, such adversarial samples are used to attack the black box target model. It is obvious that simple distillation losses are insufficient for substitute models to adequately fit the target model. This is precisely our concern. Recently, Zhang et al. Proposed a new constraint strategy, which constrains the decision boundary of each class to be more similar to the target model. However, it is poorly in target attacks, as the generated adversarial samples of the target class cannot be classified into the target class by the target network. In this paper, we further consider interclass positional relationships and achieve the alignment of the relative positions of the classes in the entire decision space. Thus, the generated adversarial samples can be also classified into the target classes by the target network. So, how to explore the decision space? In the traditional adversarial attack, such as PGD, the input data is perturbed along the gradient direction of the target class through several iterations, thus approaching the target class. That is to say, the relative positions of the clean sample and the adversarial sample in the decision space can be equally used to represent the relative positions of the two classes. Based on this thought, we designed the position exploration sample, PS, to explore the interclass relative position of the target model in the decision space, where YARB denotes an arbitrary class different from the ground truth for controlling the exploration direction, and phi is the perturbation intensity for controlling the exploration distance. By exploring the decision space from different directions, we can obtain the complete interclass topology in the decision space. Subsequently, with PS, we can design the interclass topology alignment loss to align the decision space. We first align the intraclass relationships through the knowledge refinement loss LKD. Then we generate its position exploration samples in a certain direction and compute the relative position loss LRP of the two models to achieve the interclass position alignment, where DKD and DRP are distance measure formulas. Furthermore, we can constrain the substitute model to be interclass consistent with the target model in different directions and distances, where M is the number of PS generated for a same clean sample. By simultaneously constraining these two losses, we achieve the constraint between the substitute model and the target model in the decision space. To demonstrate the effectiveness of our schemes, we compare different schemes on different target models. Our ICTA demonstrates a significant improvement with the most superior performance in target attack, especially on tiny ImageNet. In addition, we evaluated the performance of different substitute training strategies. The results show that our ICTA performs well in both targeted and non-targeted attacks and shows significant improvement in targeted attacks, which highlights the unique advantages of our ICTA. Then we exhibit the TSNE visualization of the decision space of the models. Our ICTA has a very similar topology to the target model, in contrast to all the other methods, which are very different from the target model. Finally, we conduct an ablation study on the loss functions and distance metrics. With the inclusion of LRP, there is a significant improvement in the attack success rate, suggesting that the relative position loss is indispensable. In addition, we adopt DIST as the distance metric for the loss, as it further improves the attack performance. Welcome to visit our paper and code pages. That's all. Thanks for listening.